This is where you're supposed to be, Robotics 1, and I'm Kimberly Oaks. You're going to call me Pam. Get everything coordinated here. All right. So first I'll go over just the logistics stuff so you have an idea of what the class is like, how it's structured, things like that. So my office is in WC 7006. So I do have posted office hours for Monday 2 to 4. Basically what my office hours means is that's when I'm guaranteed to be in my office available to you. But you can stop in anytime that I'm in my office. If you're not sure if I'm there, you can just send me a WebEx message just to make sure so you don't walk all the way over there. And I also have separate office hours set aside for my other classes. And you're welcome to come during those times as well. It just means that if somebody comes in for that other class, that they would get priority during that time. But you are welcome to come in anyway if you have any questions. I know, we all have weird schedules, so this might not be the most optimal time for everyone. We do have a TA who was the same TA I had last fall. He's great, Yufei Zhang. Once he gets office hours, then I'll post those as well. We'll also have an undergraduate student assistant, which will be helping out for the project portion, which we'll get into in a little bit. So for websites, as I said, Piazza is where I will post basically everything. So if you don't have access, everybody should have been added to that site. Let me know if for some reason you can't get there. There's already some resources that are available. Go ahead and look through those. If you have any questions, if anything doesn't work, then please let me know. And then for homework, all the homework is going to be done in Gradescope. So I'm doing things a little differently this fall. So the Gradescope homework, some of the questions are going to be auto-graded to help the TAs. They're definitely overworked and underappreciated, so we're going to cut them a little bit of slack. So it might be a little bit more work for you because some of the questions you're answering in there, and some of them you have to upload pictures of your work. So might be a little bit more on your end, but it'll help the TAs a lot. So if you have any problems with that, things that don't seem to be working, please let me know because it is the first time kind of trying this new format on Gradescope. And as far as course resources go, so a great suggestion from previous students, if you look in the syllabus for each lecture, I also have links to some additional material. So you're not required to buy a textbook for this class. I give you all of the notes, but sometimes there's some things that it's really helpful to have some additional resources or see things explained in a little bit different way. So I have those resources available to you through the syllabus as well. Some other things that are useful. So the robot that you'll be using for the project is Python based. So if you're familiar with Python, great. If not, there are some resources such as the Solo Learn app and talking to fellow students. So we actually have a lot of CS students in this group. So I'm sure a lot of them are familiar with Python. So if maybe you're a Mechie that says, oh no, there's coding, make friends. That's the best way to learn. So a little bit here about what it is that we're covering. So first of all, what is a robot? This is actually a very interesting question because it's such a diverse field that there's really no clear-cut definition of what a robot is. Depending on where you look, you'll get different variations of this. But for our purposes, it's basically an object that we can command in some way to do some task, right? And these robots are what we call programmable, which basically means that we can instruct them to do what we want them to do. And there's a few ways that we can do that. So the first is we have teleoperated robots. So this, if you think about when you're playing a video game and you're moving a joystick and you're directly controlling the avatar on the screen. So you can do something similar with robots. So you'll see this a lot with surgical robots. If you look up Da Vinci robot, this is a good example of that, where you have a surgeon, which is sitting with the controls and directly operating a robot. In some cases, this has actually been done across the world. or you have a surgeon, say in China, that's operating a robot that's say somewhere in South America. Right? So very, very powerful, a lot of direct control for these types of applications. You can also do pre-taught, so you'll see this in things like auto assembly and maybe say warehouses, where you can teach your robot a series of points. So maybe if it's doing a pick and place type task, you pick up from this location, you drop it at this location, and then the robot will just keep doing that infinitely. And then you can also use sensor feedback. So this is what allows us to do much more complex things for the robots. So for example, things like driverless vehicles, where you need to know what's going on with your environment. It's not like, say, auto assembly where you know what's going on all the time. You know, there's not any external things that are really changing too much. Versus if you're driving on the road, you know how complex a task that is because there's so much going on. And the best way to do that is to have some kind of sensor feedback to make sure that you're responding to your environment the way they do. So what are some of these specific tasks that a robot might do? The first I've already mentioned, something like pick and place or spot welding, where you have a specific point that you're going to each time. Trajectory following. So this is something that I will iterate a lot, the difference between trajectory and a path, right? So if a path is basically, if I go from this point to this point, that's a path. How I move along that path, whether I go quickly, slowly, that is what is known as your trajectory. And so in cases like arc welding, or maybe if you're applying adhesive or some kind of paint, actually following a specific trajectory is very important, right? So if you think about using a spray can, if you go and then you kind of stop and then you go again, or you're going to have globs of paint, and that's not what you want. So some applications, following a specific trajectory is very important. But also have things like target following. So you see this in surveillance, maybe also in manufacturing where you're trying to track something on a conveyor belt. So this uses sensors a lot to be able to detect your object and be able to actually follow that object and figure out how you need to respond. Insertion tasks. So these are used a lot in assembly. So thinking about putting a peg in a hole, that's actually a really common application. And it turns out it's a very complex application, right? So we kind of take for advantage that when we're doing these kinds of tasks, that we're sensing all of the forces and torques on our fingers, and we're able to do really in-depth things. When you're actually using robots, that's a little bit more complex, right? Because you don't have as much information as what human hands do, for example. And finally, you might also see this a lot for load handling. So especially if you look up automotive assembly, where you'll see these robots moving around, say, an entire car frame, right? So things that it would take a team of people a long time to do, and it wouldn't be very, very healthy for them to be lifting these large loads. We can actually use robots to do that very easily. And then, of course, that also comes with a lot of safety concerns as well. So actually implementing robots can be rather difficult. So some of the main components, the first is actuation. So with robots, when we look at, for this class, we'll be looking mostly at robot arms. So you can picture your arm. That is where a lot of inspiration came from for designing robot arms. So with a arm, we have links and we have joints, right? So the joints are what allow us to move the robot. And so to actually move those joints is what happens. And there's different ways that we can do that. And really depends on the application, what kind of precision you want, what kind of safety factors you want, and also how strong the robot needs to be. So some of these are traditionally used a lot, so hydraulics is pretty common, a lot more of the electromagnetics. Serial elastic is something that's a little bit newer. So historically, industrial robots have been really dangerous and really dumb. They don't know if anybody's near them, so we put them in a cage by themselves. Well, there's been a lot of interest lately in actually working with robots. So this has led to the rise of what we call collaborative robots. And so you'll see some of the robots that are designed to be collaborative. they'll use different methods to make them safe. And so one of those is actually series elastic actuators. So essentially what they do is they put little springs in each of the joints. So then if it does, say the arm is swinging around and it bumps up against you, that spring is going to dissipate a lot of that force so that you're not imparting as much. Versus say a hydraulic arm. I remember one story of a hydraulic arm that we had on campus that they attached a gripper to it. It moved unexpectedly fast. It moved fast enough that it actually sheared off the bolts of the gripper and put it in the wall, right? So that's the traditional industrial robots. Definitely something that you want to be cautious working around. But now you're seeing more and more of these collaborative robots. You look at universal robots. I'm trying to think what company bought out Rethink Robotics, but they also had collaborative robots like Sawyer and Baxter, where these are designed more to actually be safe for people to work with. In terms of sensing, so we have things like encoders. So you see those a little bit on the robots that you're working with, because basically those are what tell you the angle of the joints of your robot. So I can tell if I'm at 0 degrees or if I'm at 90 degrees. We have some way of encoding that information. We'll also be dealing with vision. So there are cameras on the robot, and we'll be going over how to calibrate cameras and some of the ways that you might use a camera to do things. There are some additional common sensors with things like force torque, LiDAR, being able to map an environment. Those things you would see more in robotics too. So a little bit more advanced sensing capabilities. And then in terms of control, so we'll be looking at both open loop planning and also closed loop feedback. So if you think about, if you're driving your car with your eyes closed and you're just going along a straight line, that'd be kind of like your open loop planning. You open just to see where you are. Basically like your closed loop feedback. So you're able to correct, say maybe your wheels are misaligned and you're actually drifting left. You wouldn't know that without having sensor feedback. Right, so it makes things a little bit more complex, but it also allows you to do things more effectively. And we'll also be covering a lot of modeling. So both kinematics, so that's being able to tell things like, depending on where all of the joints are in my arm, where is my endpoint, and vice versa. And then we'll also, towards the end of the semester, look at dynamics. So things like forces and torques, and how that affects things like acceleration and velocity of our joints. So robots in and of itself is actually a pretty difficult thing to do. So we kind of take for advantage that a lot of things we just do automatically without really thinking about it. But when we actually deal with robotic systems, it's much more complex than we realize. And some of the things that contribute to that are uncertainty, right? So we're probably used to, in a lot of classes, we have something like x plus 4 equals 5. We can just subtract out and we know x equals 1. Everything's great. We know what it is. It turns out that that's not true for most systems, right? So if you have things like sensors, you're going to notice what we call noise. So say, for example, if you have a camera and you completely block the camera, you would expect to see a black image. If you actually look at it, it's not. You're going to see little spots all over, and that's the result of noise. So nothing is perfect, and how we actually account for those imperfections is what makes robotics a little bit more complex. And then also things like delays, right? So nothing happens instantaneously. It takes time to do things like image processing. It takes time to actually send commands to a robot and execute those. So all of these little delays can actually have a big impact on the performance of your system if you don't take that into account. And then how we actually interact with the robot, right? So the way we communicate to each other, the way machines communicate to each other, very different. So having some kind of interface where humans can convey what they want to do to the robots is very important. And there's lots of different ways that this can be done. So a lot of different programming languages exist. If you get into industrial robotics, there are things like teach pendants that you can move the robot to specific positions and record those positions, have the robot execute those. With the collaborative robots, you can actually grab the robot and move it around to different locations and teach it those points that way as well. So there's a lot of different ways that can exist to communicate to the robot what it is that you want it to do. But then you also have the opposite as well, right? So how does a robot convey to the user that they're actually doing what you want it to do? Or if I walk into an industrial environment, how do I know what the robot's doing, right? So if it moves in a straight line, that's pretty predictable. If it's going something like this, I'm probably going to be scared and not want to be in the room with it because I don't know what it's doing, right? So kind of taking into account that not only do we need the robot to do what we want it to do, but we also want to make sure that people are comfortable interacting with the robot. In terms of programming, so we want things that are interoperable, which basically means that we have computer systems, software that can exchange and use information effectively. So for this class, what we'll actually be covering, so there will be some math involved. Some people get surprised by that, but because in engineering class, we will have some math. But it's not too bad. It's mostly linear algebra. If you're not super comfortable with that, come talk to me, and we'll get into whatever resources you need to help you get where you want to be for this course. But we will be looking at 2D and 3D rotations, translations, coordinate frames. So this is how we can describe how points such as the end of the robot move in relation to a point such as the base of the robot. Looking at the way we define manipulators. So a manipulator is basically just what we call a robot arm. So you'll hear that term quite a bit. Forward and inverse kinematics. So forward is if I know where all of the joints are, how do I figure out where the end is? And then the converse is the inverse kinematic. If I know I want to put my endpoint at some location, where do I need to put all of the arm joints? And how do we figure that out? Jacobian matrices and singularities. So these get really fun and interesting. It is related to, if you recall, Jacobian matrix from calculus. So it gives us a relationship between the changing in the joint positions to the changing of the endpoint positions. And we'll also go over some path and trajectory generation as well. And basic feedback, so basically be going over PID type controllers. So these are very commonly used. Proportional integral derivative is what that stands for. Really the most basic type of controllers that you'll see. And because it's basic and well understood, you'll see them a lot in industrial applications. And we'll do camera modeling and calibration. Also visual servoing. So this basically is how we can view information from the robot to inform how we want to move our robot. And then at the end, we'll go into a little bit of rigid body dynamics. So looking at forces and torques, accelerations, velocities. So because I always get people kind of confused as to, or maybe a little bit upset as to why we use so much math. So this actually, Boston Dynamics, they have lots of great videos if you haven't seen them. Fortunately, they just got purchased. They were a research facility through MIT. But what I love about this robot is that until recently, they did not use any machine learning. Right? So all of this work that you're seeing done is by understanding the math, right? So having good models, having good simulators, and really understanding the dynamics to figure out how to control the robot to do these things. And then, of course, I also love their very good videos of things not working, because that's also the reality. But especially that right there. like how many people could do that, and they were able to do that by understanding the math, right? So it is still useful. I know there's a lot of growth of machine learning, things like that, but also a thing to keep in mind is that somebody has to understand if what's coming out of machine learning makes sense, right? If you give an algorithm 3 and 2 and it tells you 6, well, if you were meaning to multiply those, it's great. If you're meaning to add them, it's not so great, right? So we want to make sure that you have some understanding of how these systems work, what the background is. So then even as we're moving more towards machine learning, you have an understanding of whether or not things are actually behaving the way you want them to. So we'll go back to some more specifics about the course. So there'll be 6 homework assignments roughly. You have the breakdowns of the percentages. There'll be a mixture of the written homework and also some coding homework. So there'll also be some questions on MATLAB Grader. So if you haven't gotten access to that, earlier today I resent the email asking you to sign up. So MATLAB Grader is an auto grader. I'm not expecting you to know MATLAB really well. This is just a way that I can kind of give you some code, and also it's good practice to figure out how to read other people's code. So there's lots of comments in there to help you for what you need to fill in. And then it auto grades, so then you can just take a screenshot showing you completed it, and that is what you upload into Gradescope for those questions. And as always, if you have any problems trying to do any of this stuff, let me know as soon as you can. There'll be 2 in-class exams, so you can already see on the syllabus when we expect those to be. And there'll also be a group project. So the group project will consist of a report, a presentation, and a small video. All of the rubrics for these are already posted. So this just gives you an opportunity to basically present the same information in different ways. Definitely a useful skill to have. And what's also great for the video is if you have a website or if you're in an interview and you want to highlight some of the cool stuff that you did, well, you already have a video where you can show that. So really hopefully beneficial to you in the future as well. For those of you in the 6,000 level, so our grad students, so OGE requires us to make you suffer more. And so to do so, you're going to have an additional homework assignment and also a research paper. So there's more details of that on Piazza, and I'll also be posting as we get closer to deadlines as well. And also, I definitely believe in transparency when it comes to grading. So also on Piazza, under general resources, you'll see a sample grade book. So at any point, you can download that. There's a separate page for 6,000 versus 4,000. You can put in your grades and you'll see what the outcome would be. When it gets to the end of the semester, the letter grade that you see on LMS is exactly what's going into SIS. So no big scares if you thought you were getting an A and suddenly there's a B or something, right? So what you see is what you get. All right. So for the project, so because there's 70 of you currently enrolled, and a little bit more than what I had last year, and we were kind of tight on presentation times, so I might allow up to groups of 5. Last year we did 3 to 4. And there's a Google sheet that's shared in the syllabus. So when you form teams, you can put in the team member names there, and that helps me to keep track as well. And then also if there's anybody who's having trouble finding team members, reach out and we can try to coordinate with different groups. So there'll be a project proposal due 10/16, and the syllabus and the project description give you a little bit more information. But basically the idea is that you're going to demonstrate some specific things. So I'm going to have you demonstrate forward and inverse kinematics, a little bit of path planning and PID control, and then you define what the other thing is that you show. So whether you want to utilize the camera to do something, maybe you want to do some pick and place type tasks, You can see in the background here, there's little blocks that came with the arms. There's also in the lab space a cupboard where I just throw random things. So there's little dice in there. So it's completely open to you to really explore what you're interested in. And so, as I said, mainly uses Python programming. If you have familiarity with ROS, Robot Operating System, you can also utilize that for this arm as well. And one thing to note is that if you change anything with the robots, please let me know. So we actually ran into a thing where upgrading the NumPy to a newer version actually broke some of the code. So make sure that you consult with me first, because then it's a lot easier for me if something starts going wrong to know at least where to look. That took the better part of the summer trying to figure that out. So I will ask for weekly updates. These are not big things. This is just to make sure that after your team is formed, that you're making some progress, right? So I don't have as much homework as some of the other courses, because I really want you to have that hands-on experience working with an actual group. So that's where I really like you to be spending a lot of your time for this class. And this is just a way to make sure that's happening. So as I said, there's a project description posted, and the deliverables will include a report, a presentation, and also a video. And where you'll be working with the robots is JEC 5312. So I believe everyone actually should have card access, and you should be able to get in there at any time. There are 8 setups, and so you can go in there, play around with the robots, and see what you can do with them. These are DotBot checks and examples from Yahoo Robotics. If you're interested in more information, I can send you the link. And there's 8 of those. The big thing is please respect the space. So these are fairly expensive robots. There's new equipment in there for the all the hardware as well. So we really want to make sure that there's no food and drink. I know this rule always gets violated. I know because people leave the wrappers on the tables. Please, if you're going to violate the rule, at least don't do that. But really that's in place because if anything happens, right, like we don't want to lose access to the space because things are getting damaged. And also, I do have a Google Sheet, which I have shared with everyone. And so the idea is that each team can put when they expect to use the space. We don't want somebody sitting in there and blocking out like 30 hours a week on one robot, right? Because we have only 8 of them, 70 students. There's going to be at least 3 or 4 teams probably to each station. So we just want to make sure that we're distributing those resources. And if we do find out that there's any students that are causing damage to the space, making an uncomfortable space for others who are trying to work there, then you will get your access revoked. And that is a very significant portion of your grade, so you definitely don't want that to happen. So just making sure that everybody's aware that we do take it seriously, that we want this to be a professional and welcoming work environment, and want to maintain that for everyone. In regards to grade appeals, so once the grades are posted, then I will allow the regrade requests for 24 hours, and then I will close those requests. So this is just so that the TA doesn't have to try and go back to something 5 weeks before they're completely done and over with to try and figure out what you're trying to tell them. Right? So we want the TAs to be able to finish up their work and move on to the next step. And I will let you know when everything is finalized in LMS, and then usually about 24 hours later, I post the grades in SIS. Once they're in SIS, that's what the grade is, unless you can demonstrate that there was some calculation error, which there shouldn't be because everything is in LMS and auto-calculated. But if you do notice something, then yes, I will change it for that. If you look at SIS and just say, well, I don't like my grade, it's the end of the semester, that's the grade. I do expect attendance. I know things happen, that's why I record the lectures, post the notes. So if you can't attend, that's fine. but do like to have a good group here so we can have discussions, dialogue as we're going through material. And I do try to make things accessible as possible. If things are going too fast or things aren't getting explained sufficiently, please let me know. I've been trying to, be more mindful of different things that I utilize in class. So like this is actually a recently found font type that's actually supposed to be more friendly towards those with dyslexia. So I'd actually like some feedback on that because I'm thinking of using that for the exams as well. So if people find this a lot easier to read, I'll transition over for assignments as well. And as far as in class time goes, if I start talking about stuff and you have no idea what I'm talking about, interrupt me, ask questions. I'm okay with that. If I'm not explaining it well, then I need to re-explain. Then there's also the other stuff that you'll see in the syllabus. Making sure you're not cheating. I definitely want you all to work together, but you should also be doing your own work as well. So are there any questions about the class structure in general? Anything like that? Yes. Will class ever be? It'll always be here. Yeah. So the first time you go over to JEC, it is a pretty small space. It's kind of unfortunate. Space is the big limiting factor at RPI. But you can have groups of 3 or 4 at each of the English stations. So maybe about a third of the class at the time can fit in there comfortably. Yeah. Right. Yep. We do have a class that's immediately after this one, but we do have a little bit of gaps beforehand. So if you have time and you want to come a little bit early for exams, I'm okay with that as well. If you require extra time or any accommodations, please let me know sooner rather than later. That'll give me a chance to set aside time near those exam times to find a space that you can take your exam. Any other questions? Yes.
So there's going to be a minimum of 14 feet.
Yeah.
Is there just one and we make a sheet there?
Yeah.
Make sure that won't go there.
Yeah, so I have a Google slide or Google Sheets that's in the syllabus. If you have a link to it, if it doesn't work, please let me know. And so what I have there is there's different pages for each station. And the first page is where you can put in all your team numbers, with whatever the team number is. And then you can go to the sheet for whatever station and you can block out. So that's reserved for you. Any other questions? Okay. So what we'll do is we'll spend the rest of class time today just going over some review of some linear algebra things. So what I learned during last year was that maybe recalling linear algebra is not as I expected as thinking. So we'll go over some of this material. Hopefully it's review. If not, then please let me know. We'll get you some resources. So some basic multiplying matrices and vectors. So typically I will use capitals to denote matrices, lowercase to be vectors. And so if we were to look at the size of these, so this is a matrix. And this could be, so this R, if you're not familiar with math notation, so this would be the set of real numbers and the size going to be m by m. What this means is m rows and columns. And so for the sizing to work out, right, this B would have to be of size n by r. So basically these sizes have to match up the number of columns, the number of rows, and the one to the right of it. And then if it's a vector, then it's going to be of dimension 1 in one direction. So what this will look like is you'll have a matrix, and this would be A11, AM1, out A10, AM. And so each of these letters is just one element of that matrix. And then our B matrix, we have similar thing. So we have and then our X vector would just be a column vector. So R rows, one column. And so we're doing our matrix multiplication. Let's say we have 1, 2, 4 multiplied by 2. So I always like to visualize by taking this and flipping it over. So we'd have 1 times 1 plus 2 times 2 would be that first element. So we're taking this, multiplying it by each element in the top row, and adding those together. And then we're looking here. We have 1 times 3 plus 4 times 2. We have, right. So notice the way the sizing works out. We had a 2 by 2 matrix times a 2 by 1 vector, and the result is a 2 by 1 vector. Right? So it's basically like these interiors kind of absorb. And so our sizing comes from these exterior sizes. And there are different things that we can do with matrices. So we can do a transpose. Right? So let's say that A is 1, 2, 3, 4. If we take the transpose, then basically we're just flipping the rows of columns. This is 1, 3, 2, 4. And there are some tricks that we can do for these as well. So if you take the transpose of 2 matrices that you multiplied together, that is equal to B transpose A. Right, so you're just flipping the order and taking the transpose. So this can be easier depending on what some of your applications. And if the matrix is squared, so the number of rows equals the number of columns, then we can also do the matrix thing. We have matrix A. We take the inverse. If we multiply the matrix inverse times itself, that is equal to I. So this I is the identity matrix. Right, and this is a square matrix. And it'll look like this. One, all along the diagonals, and then the off diagonals are all 0. So this is the definition of an identity matrix. Now you multiply or the definition of the inverse when you multiply it by the original matrix, then you'll get back an identity. And we have a similar thing like the transpose, where if we want to take the inverse of two matrices, the both of these is going to be square. And we can use the inverse. And if you don't have a square matrix, then you get into something called a pseudo inverse, which we'll be discussing at some point here. Maybe today, maybe next class, depending on how much time it takes. All right, so another thing that we'll be utilizing, which you may or may not have heard, is SVD, or the singular value decomposition. Okay, so what we have is, say we have a matrix A, we can break it down into U, sigma, V transpose. And we'll see when we start talking about Jacobian matrices that the singular value decomposition can tell us some very interesting things about our robot. So having some background of what the math is can help when we get to that. So the way we derive the singular value decomposition is the columns of U are the eigenvectors of the matrix A transpose. And then columns of V are the eigenvectors of A transpose A. And then the singular values which usually we have to know as little sigma I are the square roots of the eigenvalues of A transpose or A transpose A, because they actually have the same eigenvalues. And our singular values and our sigma matrix are put in decreasing order. And also, sometimes I tend to get a little excitable and write kind of fast. If I start to move something away and you haven't had a chance to make your notes, just holler and I'll make sure I leave it a little bit longer. So if you're familiar with MATLAB, there's a function that gives this information to you. But we'll go through a little bit of examples that can remind us that it's been a while what things like eigenvectors, eigenvalues are. So we'll look at an example here. Let's say A equals 2, 1, 0, or 3, 0. So for an n by n matrix that we'll call W, if Wx equals lambda x, so we have a matrix times a vector, it's just that vector times some scalar value. Then x is an eigenvector of that matrix W with the eigenvalue lambda. And so if we actually rearrange this equation, then what we have is W minus lambda times the identity matrix. So basically we're just taking this lambda x over to this side and pulling out that x vector is equal to 0. Okay, so this is our characteristic equation. So if we want to get u, so what we saw is that u contains the eigenvector A transpose. So A transpose, we have 2, 1, 0, 4, 3, 0, transpose that. And we do our multiplication now. So taking this times there, it goes up, so on and so forth. We get these numbers here. And then to find the eigenvalues, we can look at this equation. Right? So we want to find where this is equal to 0. So our eigenvalue we get by looking at A transpose minus lambda I. So lambda times the identity matrix means that we just have lambdas on the diagonal. So we get 20 minus lambda, 14, 0, 14, 10 minus lambda, and a minus lambda. So, getting quite a crash course in linear algebra. It's been a while if you haven't seen this. And so, from this, to get unique eigenvalues, we use the characteristic equation which is the determinant W minus lambda I equals 0. Okay, so this is the determinant. So, what does the determinant look like if we have the matrix W? And we'll just put in some W numbers here. then our determinant of W. So we take this first value up in the top, and we're going to multiply that by E times I minus F times H. And then we take minus of this next value in the top. And basically we kind of block out the top and that middle row. We do D times I minus F times D. And then we take our last column, EH minus EG. And so an interesting thing to note, what can be really useful about the determinant also in the general sense is that having a non-zero determinant means that our matrix is invertible. And so we're looking at a square matrix. There are some matrices where you can't actually perform the inverse. And a good way to do a quick check of that is to just look at the determinant of the matrix. And if it's zero, you can't invert it. If it's not zero, then you can. So going back to our problem. So looking at our matrix up here, if we take the determinant of that, we have 20 minus lambda, determinant in a transpose minus lambda I. We have minus lambda times 10 minus lambda. Minus lambda 0. So you can do a little bit of linear algebra here, combine things together. And so a little bit more review of regular algebra. So we're looking for this to equal 0. So our options are lambda equals 0, or this equation here equals 0. And recalling from high school math, our quadratic equation formula. The numbers don't really matter, but this way, if you want to test and verify, this gives you all the steps to do so. Right, so what we've learned is that we have 3 eigenvalues for this matrix. And so then to find the eigenvectors, which are the vectors that make up that U matrix, we look at A transpose minus lambda I times X equals 0. Right? So now we have our eigenvalue, lambda value. What we're looking for is these x's that match up with those. And so what we do is we can plug in, if we're looking at first lambda here, you just plug that into the matrix. And we have our x. So we know the size, that it has to match up with the dimension of our matrix here. And so that is, solving system of linear equations. So we have our x3 pretty directly. If you hold the math, you can get x1 and x2. Or you can just try to solve this using something like MATLAB. And you get x equals minus 0.174 0, 0. So one thing when we're defining eigenvectors is that usually we define those as unit vectors. So what does this mean? Is that it's actually something that I'll be reviewing again next class. Is that the norm of the vector, or basically the size of the vector, is equal to 1. This is the same as x transpose x. So it just means the way we usually define these eigenvectors is that they are unit vectors. Yep.
Finding therefore.
Yes. Yeah. So this is something that you can do very easily in something like MATLAB. You can use the function ives and get them out. I'm using this as also a way to remind you of linear algebra, how you multiply matrices, things like that. What I found last year is it turned out a lot of people did not remember doing any of this. So hopefully this is a little bit of a refresher for you guys earlier on, so you don't get lost if we use this one. So don't get too overwhelmed by the specifics. I'm not really going to be making you do this kind of stuff. This is more a review so you know what the terminology is when we actually use it to apply to our robotics stuff. But if you're interested and you work through this, I don't like to leave things unfinished. So for our other lambdas, we can get our x's. And then our last one. And so then basically our u is we just combine all of those x's together. And then you can do the same procedure to find your V matrix. A transpose A to get V. So A transpose A, 11, 11, 5. And what we'll get is our eigenvalues as first are the same as what we got for A transpose A. So with the exception of the 0 with the way the sizing works. And so we can do the same thing to get these x vectors for each of these lambda values to get our V. And then our sigma. So as we had before, our SPD is A equals U sigma B transpose. So we have our U is a 3 by 3, our V is a 2 by 2. Yep. Yes. So they do correspond to the eigenvalues. So one thing that with the sigma is that we put the scalar values and decrease the order. So the biggest one is going to go here, and then the small one. And so these need to match up with those. So you do the one that corresponds to the highest value first, and then the small one. That's why when I was computing, I went from, I did 29 first, and then I did 0.13.
The bottom one's also. Yeah. This one, that I think of it, would that some of the, what is it? The absolute value, also negative value, or would it just negative?
Your eigenvalues will be positive or zero. So since this is a 3x3, this is a 2x2, right? So sizes have to match. So we know that the sigma is a 3x2 matrix. Right, so we have 3 times 3, 2, 2, those have to match up. So our sigma is a 3x2 matrix. And the diagonal elements are equal to the square root of our eigenvalues. And we order those from just the smallest. So our sigma will then be for the numbering convention, usually lambda 1 is your largest, and you'll have up to maybe lambda n eigenvalues. And so this is square root. And like I said, now that we have each of those matrices, then we have A equals U sigma B transpose. And then we can also use our transpose term to figure out what would A transpose be based upon these matrices. So if we did A transpose, so use sigma B transpose the whole thing. Basically, we swap the order and transpose each of the elements inside. So we have B transpose, B transpose, U transpose. And so these U and V are special matrices, which we'll be talking about a little bit later. It's when we talk about rotation matrices. This is going to come up again. That actually taking the transpose and then taking the transpose again, the transpose is actually the same as the inverse. So these actually cancel out. For this special case. And then just because you might have heard this term before, if we do A transpose times K, we have B sigma transpose U transpose U sigma U transpose. So it turns out that U is also one of those special matrices where U transpose times U transpose is the same as the inverse. So these actually cancel out to identity. And so we get U sigma transpose, sigma B transpose. And so if you actually multiply these out, right? So if you have this matrix here, and you transpose this times it by itself, that basically we just get square root of lambda 1 times square root of lambda 1, square root of lambda 2 times square root of lambda 2. Right? So this is just B and then the square matrix of the. And so this is what's known as the eigen decomposition. Of A transpose. So not something to talk about, but give us a chance to review some of these little things. Right. So they're orthonormal matrices. So this is what we're going to see when we start talking about rotation matrices. And so what it means is that the columns of the matrix are orthogonal to each other. But that means if I take column 1 and I transpose it, multiply it by column 2, it'll equal 0. And it's normal. So if I take column 1, transpose, multiply it by itself, it'll equal 1. So very special case matrix. And when we get into rotation matrices, they allow us to do some very interesting things to vectors. Right. So if you recall doing bases of spaces, it's basically your orthonormal matrix is composed of the basis vectors. Largest to smallest.
So when you become to lambda,
Mhm.
they are always going to always upward is always. From the lambda for base, from the lambda for the
Right. So yes. So the lambdas for A transpose A and where's it here? And here it should be. Very good. My apologies. Yeah. So it turns out it's a special case with matrices when we do look at the eigenvalue A transpose A transpose those eigenvalues.
time.
Right. So for actually calculating those U and V, you have to because they'll be different eigenvectors, but the eigenvalues will be the same. That's why we didn't really need to read out the very. So I'll do. We'll save this one for next time. And we'll look at a couple other useful definitions that we'll see on occasion. So the rank of a matrix is equal to the number of linearly independent columns or rows. And it's also equal to the number of non-zero singular values in our singular value decomposition. So it's so a little bit more math notation here. So what this means is A is an element of the set of real numbers that are size n by m. So basically, A is an n by m matrix of real numbers. So if we have that case, then the rank of our matrix is less than or equal to the smallest of the number of rows or number of columns. If our rank is equal to that minimum value, Then A is what we call full rank. Otherwise, we call it rank deficient. And so some of these terms will make more sense as we start talking about things like our Jacobian matrix. This also comes up when you start talking about grasping, that thing that I also, at least when I thought it was covered in robotics too. So that can lead to some interesting observations as well. And one thing to note is only the zero matrix has rank 0. So the smallest rank in any matrix with any non-zero number can be is a rank 1. So what's an important thing with this idea of a rank is that if A is a square matrix, then our inverse exists only if A is full rank. So this also comes back to our SPD, that if we don't have 0 singular values, then we also know that we have an inverse for our matrix. Then some other interesting tidbits: if we have B is an n by k matrix, and if that has rank n, so basically this is full row rank, and the rank of A times B is equal to the rank of A. If we have a matrix C, we'll say it's L by n. And let's say that this has a full column, right? Then the rank of C times A is the rank of A. And the rank is also equal for the transpose matrix. So just in this one little thing here. So kind of looking at an example of how we would determine rank. Let's say we have 1, minus 2, 3, 0, minus 3, 3, 1, 1, 0. I'm going to call this column x1, this column x2, this column x3. And so this matrix is rank 2 because column 3 is actually a linear combination of columns 1 and 2. Or x3 is actually equal to x1 minus x2. And you can also verify this using Gaussian elimination. So you can take rows and automatically subtract them to other rows, and you'll get down to wait for this whole bottom row to be all zeros, and that's how you know that you have only rank 2. Okay, so are there any last questions? I know it's hot and everybody's getting ready to not be in this room. Yeah. Yeah. So there's a lot of different ways to figure out. So